Hey y'all, it's your math teacher, Mr. Boyd, back at it again, and today we're going to be looking at the law of cosines this time. It's similar in many ways to the law of sines from the previous video. The formula is different, but in terms of what it's useful for, it's the exact same thing. We're going to be finding missing angles and sides of triangles which are not right triangles, okay? So what we're going to start out today, and I'll zoom in here in just a second, is let's take a look at the actual laws themselves. I want to give you a second to write those down. When you're ready, hit play again. So you need to pause now. And what I want to show you is that what's important about these is not the fact that you memorize that it's A's and B's and C's and all that. What you need to recognize is that whatever two letters are here, in case it could have been X and Y, it could have been anything, it's the same two letters right there, okay? And whatever this letter is, it's the angle that corresponds to it there. In the alternate form of the equation, it's the exact same thing. Okay, if there's a B and a C right here, well, guess what? There's B and a C right here. See the similarity? And if we have angle A right here at the beginning, we're going to have an angle A, or a side length A, excuse me, right there at the end. So what are these for finding? Like, what's the purpose? Well, here's how we know. You see how in this one, the thing that's nearly already isolated is little a? That tells us that this is useful for finding side lengths. And again, guys, totally arbitrary that that's an A. That could have been an X, or it could have been anything. All it is that if this is whatever two letters are here and here, it has to be there as well. What about this side? The thing that's almost already isolated right there is a capital letter, so this is useful for finding angles. So, I do want to try to fill in this little sentence stem here. Based on the law of cosines formulae, I believe it's useful when we know, well, let's look at the side on the left. What information is known in this scenario? In order to find a side length, you need one side length, another side length. Okay, I'm going to make a note of that. We need two side lengths. So two sides. And one angle. But it's more specific than that. Okay, look at where B and C are on a triangle diagram. You've got B right here and C right there. Angle A is the included angle. So two sides and the included angle is what we need. Now the other thing that would work, let's look at this formula on the right. In order to find an angle, we would need to know 1, 2, 3 sides. That's it. So, or we could know all 3 sides. Okay, so that's how we know when to use it. Let's go look at how to use it. Okay, here's our first example. We're going to have to solve the triangle. I want you to get in the habit of asking yourself, do we meet the criteria to use the law of cosines? So let's see. We have a side, we have the angle in between, so yeah, you bet we do. Let's set it up. And guys, I'm not going to use the letters. Let me show you what I mean. All I have to do is say, what do I want to find? Well, hold up a second. We set up here that if we wanted to find a side length, we would be finding the one that was opposite. So if we want to find a side length, we'd be finding the one opposite from the known angle. Let's go back down and see what that looks like here. So the known angle is C. So guess what we're going to find? We're going to find side C. So C squared equals the other two squared. So 19 squared plus 26 squared minus 2. And remember we said above, it's going to be the same exact 2 again. So 19 and 26. And then cosine of the angle. Now, I want you to be as efficient as possible about this. So what we can do, let's get rid of this square right here, which means we'll take the square root of both sides. That way, everything gets typed in the calculator all at once. So there's my square root. I'm going to type in 19 squared plus 26 squared minus 2 times 19 times 26, and then we'll finish it off with a cosine 42, and we'll see what we get. All right, 17.4. So C equals 17.4. Okay? And then it says solve the triangle, so I need to find angles. I like to do them in order, so let's solve for cosine of B. Cosine of B is going to be, well, guys, honestly, here's what I do when I set these up. I don't even look back at the formula. What I do remember is some of the key features of it, though. So what I remember is that in the numerator, there were 3 things, and they were separated first by a plus, then by a minus, and each of them are squared. And then in the denominator, there's always a 2, and then 2 numbers. And I remember that we said the thing that goes here, its corresponding or its opposite part will be here. So if that's angle B, we need side length B down here. so that's 26. And then I can just pick the other two sides. The order doesn't matter. So we'll put in a 19 here and a 17.4 there. So 2 times 19 times 17.4, and it's totally calculator time. Now, guys, there's something that a lot of people are going to mess up when they do this. They are going to type in this chunk right here, and they're going to wonder why they got a ridiculous answer. Notice over on the left side, there's a cosine sitting right here. So you're going to have to do a cosine inverse of that whole thing. So I'm going to go over and do that now. So cosine inverse, looks like the thing inside the cosine inverse is going to be a fraction, so I'm going to get myself set up with a nice fraction here, and let's start typing. So 19 squared plus 17.4 squared minus 26. I'm going to press, I almost forgot to square it, don't do that, and then go down to the denominator, and 2 times 19 times 17.4, and boom, 91 degrees. Does that angle B look like it's about 91 degrees? Yeah, I'm thinking so. And I'm going to leave it as a whole number. You know, let's do best practice. Let's do 3 digits. So 91.1. We were asked to solve the triangle. We know all 3 side lengths. We know 2 angles, and we would like to know the third. So all we're going to do is we're going to remember that a triangle has 180 degrees in it. So 180 minus 42 and minus 91.1. And we are going to be done. 46.9. And in my class, when I'm grading, I will accept a complete labeled diagram for full credit when a diagram is given. So that completes the question. Let's try another one. Ooh, what about this one? In this one, they don't give us a picture. So guess what we get to do? We're drawing our own. Now, notice, I'm not going to put really any effort into this picture because I don't need to. 7, 9, 13. No rhyme or reason for that. What I do find to be useful, though, is if I put letters on here, because if I don't put letters on here, then a lot of times when I find an angle, it's not clear to me which one I found. So let's go A, B, C, and let's go find some angles. So we can just arbitrarily pick which one to find first. I think I'll do A because it's nice to do it alphabetically. So cosine of A equals, and then again, guys, I'm not being silly here. I genuinely do it this way every time. I remember that there's 3 things that are squared. Once I write those all down, I say, hey, that's A, so the thing at the end must be A. So that's 9. The other 2 don't matter. 7, 13, 2 times 7 times 13, and booyah, calculator time. Now, it's all the same stuff. These button presses should start to feel really familiar after you've done just like 1 or 2 of them. So, I've got something highlighted here. So I'm going to get my fraction all set up, and I'm going to start typing. So that's going to be 7 squared plus 13 squared minus 9 squared, and the bottom 2 times 7 times 13. And boom, 41.2. So A is going to be 41.2. If it's 41.2, they ask for the nearest degree. So I'm going to say that A is 42. Let's go to B. Cosine of B, going to be very similar. In fact, it's basically the exact same setup. We're just going to rearrange the numbers a little bit. So for B, I'm going to identify the side across from B. That's 7. I'm going to write that down here at the end. That means there's a 9 and a 13 in here. So 2 times 9 times 13. And guys, I am really sorry that this video ends up getting a little bit more boring than the others, just because I know it's probably similar to watching paint dry to watch me type these in all day. But I do need to type them in. And I do want to show you that on the Inspire, you can see if the calculator interpreted right. This is one of the things I love about the Inspire is you get a lot of confidence in your answer because you can see exactly what the calculator thinks you meant, and it will tell you if you have misinterpreted what you're typing in. So get my denominator, 2 times 9 times 13. And let's see what we got. We've got 30.7. We're going to round that. So we're going to say that B is 31. And then I'm going to take the easy way out at the end here, y'all, because we know that a triangle's angle sum is 180, so I'm going to go 180 minus 31 minus 42, and What do we get? We get 107. And so I'm going to call that good. They asked for the angles to the nearest degree. We just did that. We're all good. Let's look now at a simple example that actually does come from real life. In this one, we've got a railway company that wants to put a rail line going through a mountain. We actually have done this in our state. If you ever drive through Snoqualmie Pass, you'll see train tunnels going through mountains. Even in the city of Tacoma, we have an area down by Ruston Way where our train line running through town goes basically through a hillside. Why do they do this? Because trains aren't very good at going up steep hills, and going all the way around a mountain range is not typically feasible. So what they end up doing is they just blast right through it. So what they would want to do, though, is they would want to know how long that tunnel has to be, because that's going to tell us how long it takes to build it and how much it's going to cost. So what they'll do, they'll bring in a surveyor who will take measurements. And in this case, they'd say, well, we want the tunnel to start here and end there. So they'd find some point where they could stand off to the side. They would take these two measurements, they'd find the angle between, and now we can see this is law of sines, cosines, because we have two side lengths and the included angle. So the setup's pretty easy. I'm going to call it t for tunnel. So t squared equals 388 squared plus 212 squared minus 2 times 388 times 212 cosine of the included angle, which is 82.4. Now remember, this is the mistake a lot of people make. They forget to square root both sides. So please do that. And once you get that set up, it's just a calculator exercise. So let's go type it in. Let's practice. Make sure you know what you're doing. Whatever calculator you have, or whatever calculator you're using, I want you to take the time to actually practice it. Every year, I see students who, in class, they go, yeah, that's okay. I don't need to do it. Everybody else can type it in. I'm not going to participate. And the sad thing is, they don't realize what stumbling points they're going to have. And so what typically happens is they end up finding that those are the issues during a test, and that's very sad for their grade, and I would not want that to happen to you. So please practice typing it in the calculator as I am right now. Okay, and I'm almost done here already, so I'm going to toss a cosine 82.4 on the end of this thing. And boom. Take a look at the picture. Is it reasonable that we could have a 417-foot tunnel on this diagram? Heck yeah. So 417-foot train tunnel. Done. This example comes straight out of our textbook. It's actually one of the exercises in this section, but I like it so much that I wanted to include it in today's video because I think it makes a really good example of an application of this learning. So here we go. We have a 100-foot vertical tower. Looks like maybe it's a water tower or something. It's going to be erected on the side of a hill that has a 6-degree angle. So there it is. You can see it's going on a hill. And it's a 6-degree angle with the horizontal. We see the 6-degree angle. Find the length of each of the two guy wires. That's this wire and this wire there, which we do really use in real life to keep towers and things from falling over, particularly like telecom towers and things like that. And they're going to be anchored 75 feet uphill and downhill. They were kind enough to label that for us from the base of the tower. So what we have to think about here, guys, is we got to think about this as there's two different triangles going on here. So there's one that comes from the top of the tower down and then over to here and connects with the wire. And there's the same exact one. I'm going to trace it here that goes over to the right-hand side. So I'm going to start by working on the one on the left. In fact, I'm going to try to draw it. And I'm not going to be real picky about how I draw it. They said we want to know the length of the guy wire. They told us it's a 100-foot tall tower. And they told us this is 75. I'm wondering, do we know this angle? Well, first of all, just look at it. Is it right or obtuse or acute? So it would be a right angle if it were this dotted line right here. Well, how big is this angle? That's 6, and that's 90. So this is a 96-degree angle. So let's see, is this a law of sines or a law of cosines? Well, we have two sides and the included angle. So this is clearly a law of cosines question. Let's set it up. So I'm going to say x equals, and I'm going to go right to the square root on this one because we've seen in the last few examples that's what we need to do. So here I go. I'm going to have 75 squared plus 100 squared minus 2 times 100 times 75 cosine of 96. All right, and we are right into the calculator. That's one of the things I really like about the law of cosines is there's not a whole lot of algebraic manipulation that needs to be done. And from a student or from a new learner perspective, it's pretty convenient because there's not a whole lot of places where you can get it wrong. Now, I'm not saying that it's easy because there are things you can get wrong in your setup, But it's one of those deals where if you have good calculator skills, and if you understand the concept so you can set it up correctly each time, you're going to find really good success with this. So let's see what we get here. We get 131 feet. Let's see, does that make sense? Yeah, it seems to. This one seems to be, and they tell us how to round it. They didn't, so we're going to use 3 digits. So 131 feet. That's our first one. Oops, I didn't mean to cross that out, sorry. Meant to put a line here to separate the calculations. Now we're going to focus on the one on the right because it looks like maybe it's shorter. So I'm going to draw this one now. And so we want to know how long is the wire. We're told that this one is 75. We're told it's still the same tower, so it's still 100. And are there any angles here that we know? Well, let's see. This angle, if it existed, because this angle was 6, that would have been 6. So this angle inside the triangle, now it's acute, it's 84. So you see in this triangle it was 6 degrees more than a right angle. Here it's 6 degrees less. So guess what? It's the exact same calculation as before. That's not a 1, by the way, that's an angle marker. It's the exact same calculation before, now there's just an 84 in it. So if you have a TI Inspire, please do this. I've pressed the up arrow twice. I'm going to highlight this, and I'm just going to come back in and edit it because the rest of the setup is, I can already identify, guys, I hope you can too, because it's the same side length, just a different angle. The side length part of the setup is going to be the same. So I'm just going to go in, and instead of putting in 96, I'm going to put in 84, and I'm going to hit enter again. Let's see what we get. We get 118.5, so I guess I should actually round to 119. Now see if that makes sense. The one on the left was 131, there was an obtuse angle. The one on the right's a little bit shorter at 119. We can even see that visually. But what I hope is also clear is that I didn't even have to write the setup to get this second one, because I can recognize based on the side lengths, it's the same setup just with a different angle, and that's the quick, easy way to do it. One of the things that's really imperative for your success in these is the fact that we are not going to tell you on a test ever if it's a law of sines or cosines question. I really don't know of any teacher or any standardized exam that does that. So we have to be able to look at a picture like this one and identify what an appropriate strategy is. So take a minute, see if you can tell if this is a law of sines or a law of cosines question. Guys, this one's definitely going to be a law of sines, and here's why. We said with cosines, one of the ways to solve a question is if you know all 3 side lengths. We don't have that. Or maybe you know 2 side lengths and the included angle. We don't know 2 side lengths. So it's definitely not cosines. And it is sines because you have something in its opposite and something in, well, wait a minute, is it really? Here's what you do if you're not sure. Let's say you struggle to figure out if it's sines or cosines. Think about which is easier to set up and do. It's a lot quicker to set up sines. I'm not saying it's easier, but it's quicker. So let's try setting it up. We want to find x, so we'd say side length x over sine of 1/16 seems promising so far. 19 over sine of, uh-oh, we're missing this side length. Does that mean we're dead in the water? No, we're just going to have to go find it. So 180 minus the other 2 angles, and I'm going to add them together, so 146. And out of that, we get 34 degrees. And so all we'd have to do is multiply that up and type it in. Let's look at another to see if we can practice identifying if it's a sine or cosine question. No, try again. Maybe pause the video, maybe try setting it up to see if you're right. Does this look like it could be a cosines? Today in class, my students thought it probably was cosines because they saw in this example that 2 side lengths were given. They thought, ooh, that makes sense. We learned earlier in the lesson that 2 sides and 1 angle. But remember, in order to use cosines, it has to be 2 side lengths and the angle formed by them, or the included angle. And we don't have that. But what we do have is a side length and its opposite, and another side length and its opposite. Absolutely law of sines. This will be our final question today. A plane flies north from Yuma, Arizona to Salt Lake City, Utah, a distance of 150 miles, turns right 50 degrees, and travels 100 miles more before landing in Denver. How far is Yuma from Denver? All right, guys, the trick on this one is in the question, okay, and in the diagram. If you can get the diagram, the math is really pretty easy. In fact, law of sines and cosines is very much that way. If you can understand the diagrams and the setups, you're going to be really successful. So let's try drawing this one. A plane flies north from Yuma to Salt Lake City. So that's my best attempt at north, 150 miles. Let's do Yuma to Salt Lake City up there. Then turns right 50 degrees. This is the part that people always get wrong on my test. So, guys, look. if that was north, 50 degrees away from north, you would probably know is something like this. A 50-degree turn to the right. True? That seems pretty intuitive. It's 50 degrees away. So why is it then that every year when I give a question on a test, people draw this? That's not a 50-degree turn. If this is north, and you're now going this way, that's actually an obtuse angle that you've turned through. That's not a 50-degree turn. Okay, so be really, really careful. I'm trying to point out the mistakes that students have made in the past. They've made the mistakes. Now you don't have to. We've already identified here that if north is here, 50 degrees to the right looks something like that. So if that's 50 degrees to the right and it goes another 100 miles, where's the 50-degree angle? Well, it's right there. That's the 50-degree angle. And the reason that's important is because if you know that angle, you can find this angle. These two are a linear pair, which means they're supplementary. They add to 180. So that angle inside the triangle is 130. And from here, we can set up, wait a minute, is it law of sines or is it law of cosines? We have two sides. This angle is the angle that's between them. So this is law of cosines. I'm going to drop an x right there so it's clear what it is we're finding. And we're going to say x equals the square root of, let's try setup, 150 squared plus 100 squared minus 2 times 150 times 100 times cosine of 130. Go ahead, take your time, type it in. 150 squared plus 100 squared minus 2 times 100 times 150 and a cosine and a 130 and how far is it? 227.6 miles. You should always double check two things before you submit an answer. Say, first of all, does what my calculator says right here, does that match what my math on my page said? Check. Yes, it does. Number two, does the answer I got make sense in context? If that's 150 and that's 100, that's 227. Heck yeah, we're done. Guys, hope you enjoyed the video. I hope this is going to be helpful, and I hope you nail this upcoming test. We'll see you next time.